again before I forget. So that means we're going to kind of wrap up gradients. I can go down to the lesson outline here and talk about, what do we actually do with the signal that we are collecting? So far we've been kind of talking about signal as just a general concept, but how does that actually create an MRI image? We'll jump into that today, and we'll kind of start putting together these pulse sequences as well, which if you're not familiar with, I guess you will be at the end of this class, but I don't want to get ahead of myself. So let's jump into gradients first and finish up that section. So this is where we kind of ended last time with the concept of how we use gradients to spatially encode spatial information in the signal that we're collecting from MRI. I'm getting a notice my internet connection's unstable. We already knew that, but thanks, Sue. Okay, so we have this strong magnetic field like we talked about last time, tens of thousands of times stronger than Earth's magnetic field. And it's generated by a superconductive coil, the main magnetic coil in the MRI machine. And that typically has a uniform intensity. So 3 Tesla might be kind of common wherever we're doing MRI scanning, but there's other field strengths as well that are used quite often. And what we want to do is modify the strength of that field for different hydrogen atoms, depending on where they're located in our object of interest. For me, in my research, it's the brain. For others, it could be the abdomen or the knee or what have you. We want spins or hydrogen atoms at different locations in the body to precess at different frequencies. And if we modify this field strength, we can modify the precession frequency thanks to that relationship with the B0 field. And that's defined by the Larmor equation. I would love to get rid of this gray box in the middle of my screen. It's not showing up on my tablet. So, sorry, are you guys seeing this gray box on the Zoom call, or is it just me?
I see it.
Thanks. Oh, no. All right, well, this is just all a travesty, isn't it? I'm going to have to start Googling, hey, it went away. All right, cool. Can we get back to not having the controls visible? You'd think all of this stuff would show up at the first session, but not the third one, but you live and learn, I guess. Okay, so back to the Larmor frequency and how we're modifying the precession frequency of our hydrogen atoms. If we can overlay a gradient field, which is a very weak magnetic field that's superimposed on top of the B0 field, weak relatively to the B0 field, it's usually like 1% of the magnitude or less. We can modify the precession frequency. That's kind of what I'm showing in this figure that I made a while ago on the right here. So hopefully you guys can make it out, but if not, there's kind of a negative lobe of the gradient over here that's causing the spin on the left to precess at half the rate of the spin on the right in this very exaggerated example, just kind of a pictorial example. So we talked last session about how we can use this both for slice selection and frequency encoding. And just kind of briefly talking about that again, if we modify the precession frequency of our brain, for example, from top to bottom, then we have layers of hydrogen atoms that are precessing at different frequencies. And when we apply our B1 field, we can tip the net magnetization from that slice only, thanks to the resonance condition that's required for MRI to function. You need to apply that B1 field at the same kind of frequency as the precessional rate of hydrogen atoms in order to actually exchange energy and tip the NMB. So that's slice selection again. And then frequency encoding, as showing, if we apply a different magnetic gradient that's actually going across the brain or object of interest, then we can get spins to precess at different frequencies. And when we actually measure our signal, we can look at what different frequencies are actually contained within that signal we're measuring. And we'll kind of get into how we do that today. And once we break it apart into different frequencies, we can look at kind of like the amplitude of that signal and get a sense of, how many hydrogen atoms are processing at what frequency. And that'll kind of become a little more clear when we talk about some of the stuff right away in this session, especially the Fourier transform. But we have one more dimension that we haven't spatially encoded yet. That is conventionally the y direction, and we do that through phase encoding. So let's talk about phase encoding. And again, if anyone has any questions about gradients, let me know. They can kind of take a bit of time to get a sense for, but hopefully I've been relatively clear so far. Okay, so when we're applying another gradient, this time to distinguish between hydrogen atoms at different locations in the y direction, which would be kind of from top to bottom of this diagram or from back to front of the brain. In the brain, that's definitely a brain that I've drawn. If we apply a gradient in that direction, like I've got with those two purple triangles on the right side of the screen right now, we will get, again, differences in precessional frequency, which is great. That alone can help us to distinguish between spins at the back of the brain and spins at the front. But the problem here is that we've already kind of set frequency information in our resultant signal to tell us about differences from the left to the right of the brain in the x direction. So we can't kind of use frequency in the x direction and frequency in the y direction because they kind of they muddy the signal a lot, and we can't tell whether we're seeing more frequency or more amplitude in this certain frequency based on locations of spins in the x or y direction. So basically, there's just no way of distinguishing between the two axes if we use frequency encoding for both. So what we do instead is we use a separate kind of spatial encoding by encoding phase into our spins in the y direction. And again, this is convention. You might find applications where frequency encoding and phase encoding are switched, but for the purposes of this course, those are not very common. So how we do this is by applying a gradient in the y direction, like I've got drawn here, and then we wait a period of time on the scale of some milliseconds. And then at the end, we will see, oh, good thing I thought about this. I actually have it drawn wrong in my notes. We will see something like this. So assuming that all of our spins are processing in the clockwise direction for our purposes, I'm just going to draw our 9 dots here. And the arrow is just representing the phase of their cycle, like where each spin is in their precessional cycle. So the ones at the top, because they have been processing at a higher frequency, they've been processing faster than the other spins in the diagram. These ones will be actually ahead in their precessional phase. They'll actually have spun farther than the middle row if I'm using them as a reference and say, okay, we've waited an amount of time where the middle row has been unaffected and it's processed as such that it's back at its original position. When the middle row is at that original position, the ones above it, the spins above it, are going to be ahead in phase. So they've actually processed farther than the ones in the middle. And similarly, the spins at the bottom row here are going to have not processed as far as either the middle row or the top row. So they're going to be behind in phase, right? So I can label that here. I have a pink marker for the ahead for some reason. Okay, so this set of spins up here is ahead in phase. And then the middle row is normal, which I've got as a dark green. And then the bottom row is behind in phase, which is a blue. Let me know if there's any questions about that. But in this way, we can now look at the frequency of signals that we're seeing to distinguish between spins that are located in the x direction. And we look at the phase of those signals to tease apart where spins are located in the y direction. So we're encoding spatial information in two different, related but independent ways. And that helps us to kind of tease apart these different directions in our resultant signal. So what this would actually look like in the black axis at the bottom, if we had a signal from our kind of normal group, which I've drawn 2 cycles here. So say when we're recording our signal, it looks something like this for the spins in the middle. So 2 cycles, right? Then if we look at the pink phase, the ones that are actually ahead in phase, the signal from that small subpopulation of spins will look like this instead. I guess that'd be up here. So you can see that compared to the green signal, the pink signal is ahead in its precessional phase, or just in its cycle, because essentially it's getting to any given point before the green signal is. So you can see it starts at the top of the peak of its amplitude, whereas after a certain amount of time, the green signal also reaches the peak of its amplitude. So the pink, again, is ahead in phase. And then just to kind of fill this out for everybody, the blue signal in this example, that again is very exaggerated, but hopefully helps to make things visually represented as well. Yes, clear as mud now, right? The blue signal is behind in phase. It's taking longer to get to any given point than the green and pink signals are. So obviously, this looks very messy, but using fancy math, we can kind of actually separate these signals that would in reality be overlaid and all sandwiched together into some sort of resultant signal. And we can identify signals that are occurring at different phases, and then use that information to infer information about the populations of spins in the y direction. So that's phase encoding. And with that, we've covered all 3 directions of spatial encoding that we need to in order to actually collect an MRI signal. Another important note about phase encoding, and this will become more relevant during our pulse sequence diagrams discussion later in this session, is that phase differences are persistent. What that means is when you turn the gradient on for phase encoding, you immediately start to see some differences in phase, just because some spins are processing faster, some are processing slower. And then by the end of the time you've applied the gradient, for the desired duration that you want, you can turn that gradient off, and every proton, every hydrogen atom is going to return to processing at the same frequency. And that means that the top row of spins here that's ahead in phase is always going to be ahead in phase, because there's never going to be a time in this example where the other 2 rows of spins process at a higher frequency and therefore kind of catch up in phase. We'd have to apply a negative gradient, or like the opposite gradient, in order to reverse that phase encoding. So this is important because this means we can encode phase information to our spins whenever we want. Whereas with frequency encoding, we only see those differences in precessional frequency when that gradient is actually on. So that is an important difference between phase and frequency encoding. Phase encoding is, it's incited by a gradient. You cause it with a gradient, but it remains after the gradients turn off. Whereas frequency encoding is completely dependent on when the gradient is on. And as soon as you turn the gradient off, the spins go back to processing at the same frequency, and you can no longer tell the difference between them with frequency by looking at the frequency of the signal that you're measuring. Sorry, I've said frequency and phase a lot at this point, but it all makes sense if you go back and check the record, I promise. Okay, so let me know if there's any questions about the 3 different types of spatial encoding, and with that, we'll move away from gradients and talk about kind of how they're applied and how we make sense of this signal that now has different frequencies and different phases and all this fancy stuff. So this is one of my favorite figures from that textbook that I recommended last time, this MRI Principles and Applications textbook. It helps us to kind of understand how in the world we can make sense of all this signal that is now, one line, like the solid black line in the middle, but it's made up of all of these different sub signals with different frequencies and different phases. It turns out you can tease these apart, again, using fancy math that we'll jump into next. But I like leading with this visual because it kind of highlights how on this page there are many different sine waves shown. They're all sine waves with just different frequencies. They all have the same amplitude, meaning that the peak of this sine wave is always at the top of that figure and the trough's at the bottom. They have the same amplitude. But the frequency, the kind of, I guess I'm thinking about defining frequency. I guess I will because I've paused now. Just the amount of times that this sine wave cycles or completes its cycle in a given amount of time, that's different between the waves here. And they all have different, dotted line appearances, which are kind of hard to tell the difference between. But just by kind of looking at the page, you can get a sense of how these signals might sum into the solid, bold line, the actual signal, which is a sinc function, right? Which we don't really need to worry about the minutiae of what a sinc function is. But you can see that there are these frequencies that are very highly positive at one point, and others that are kind of canceling them out because they're very highly negative at the same point. And that's why most of the signal we're recording is somewhere in the middle of the page or in the middle of this figure. It's all like relatively low amplitude compared to the signals that comprise it. But ultimately, these things add together and produce one signal that we can measure. And this is how it works in MRI. Not with this exact appearance of a signal we record. We'll get into that later as well. But you have many different, subcompartments of signal with different frequencies and now different phases that all add together into one, bold line signal that we're recording. And then we have to kind of tease that apart and break it into those subcompartments to make sense of where is the signal coming from in the brain. Okay, so to answer the question, how do we make sense of the signal? What we do is we use this thing called the Fourier transform. And again, math is very important to MRI, it turns out. But in terms of understanding the intuitive explanations for MRI, as best as I can explain it to you, I like to kind of gloss over a fair amount of the math because it can definitely, you can get lost in there fast. So the Fourier transform, though it is very important, and thus I'll kind of give you a brief on what it is. I'll start with a disclaimer that I've taken 3 graduate level courses on MRI physics. One of them was like a dedicated MRI physics course, and not once did I see the Fourier transform actually drawn on the board or like in a slide. So I never actually learned like the specific equation or function of the Fourier transform, which probably means that you don't need to know it either. If you do, then maybe you should be teaching this course instead of me. So I'm going to leave the Fourier transform with the description that this is a mathematical function that can take a time-varying signal or a time-varying function, it's a signal in our case, and move it or kind of represent that same information in a frequency space, which if you're not familiar with frequency space, that's okay. First time that I learned about it was in my master's as well. All it essentially is a different way of representing, a time-varying function like a sine wave. So the frequency domain is at the bottom of this figure that I've pulled from a very handy website. That's the frequency domain there. And you can see that there's these arrows in the middle of this figure here. The FT and IFT, that stands for Fourier transform and inverse Fourier transform. And it's essentially transforming the function on the left, which is in the time domain, into the frequency domain. It's the exact same information, but it's represented in a different way. So instead of, at the bottom of this time domain figure, we've got an axis representing time, right? Over a period of milliseconds, the signal is getting stronger and weaker and wobbling back and forth. Whereas in the x-axis of the frequency domain, we're representing differences in frequency instead. So time is not in the picture anymore. what we're looking at is the signal that we've recorded across time, so the whole thing, and we're breaking it down into the signals at various frequencies that are composing that one function that we put into the Fourier transform. And you can see those above. I've kind of skipped over this, but that's these three signals, A, B, and C, up here. They're getting added together to create that function at the bottom that we have put into the Fourier transform. And these get separated and teased apart into the frequency domain using the Fourier transform, and they're represented like this down at the bottom in the frequency domain. Now, I'm actually going to circle the other side just to cross this out. We can, for our purposes, for MRI, we can essentially ignore everything that's represented as a negative frequency because the outputs of the Fourier transform are symmetrical. We don't need to go into why, just because that gets into the actual math behind the Fourier transform. I did look it up and decided that it wasn't really worth mentioning. Essentially, the Fourier transform outputs are symmetrical, so we can just look at positive frequencies, and the negative frequencies are representing the exact same information. So we can see here that there's bars at different locations on the x-axis that represents different frequencies. So you can see that the green function C on my screen, it has a small bar at the lowest frequency of the three that we have drawn here, right? It's got the smallest amplitude and the lowest frequency. Whereas the next signal that I'm going to talk about, the signal B, the blue one, that frequency is represented to the right of the green one, meaning that it's a higher frequency. The wave is actually cycling more often, and it also has a taller line, meaning that the signal is present in higher amplitude, right? So the function here, this blue line, the height of it is determined by the amplitude of the signal, which is essentially difference from trough to peak, although it could also be just from 0 to peak or 0 to trough. It's all essentially the same. For our purposes, we don't need to get into the specific details, but that's what determines the height of the line, is essentially the amplitude of the signal that we're looking at. And extending that, you can see that signal A, the orange one, has the highest frequency here. It's cycling the most in a given amount of time, so it's represented furthest to the right in frequency space, and it also has highest amplitude. The wave is actually bigger in the orange line than any of the other ones, so it also is represented by a higher line in frequency space. And that is essentially what we need to understand about frequency space, is basically how it's representing subsignals in our image. And hopefully you can kind of see how this might be useful when we are looking at trying to break down that that bolded sinc function that I had above into its component signals. Now, if we put in that black line function that we've got here, we put it into the Fourier transform, we will get a bunch of functions or delta functions in frequency space, or essentially just those lines at different frequencies with various amplitudes, and that will tell us which signals are present in this bold black line function here, and what amplitude are they at. In case you're wondering, the amplitude or the size of each of the lines in frequency space for this function that I've got on the screen now, they would all be the same height. And that comes back to what I mentioned before about how all of these sine waves have the same amplitude, right? They all go to the top of the page and then they go back down to the bottom of the page with their peaks and troughs. So that is a brief crash course on frequency space, and we'll be using this again today, but hopefully that is kind of enough for you to understand what the Fourier transform can do for us. It'll take a time-varying signal, or a signal that we are viewing in the time domain, and it will represent it in frequency domain. Now, I'm sure some of you are wondering about how I haven't mentioned phase information at all, and I'm probably not going to, unless somebody has a question about it. And even then, I'm probably going to need to bring it up again next session, just to make sure that I have a clear explanation for it. The Fourier transform in MRI does also tease apart differences in phase of signals. But there's a couple issues with that here. One is that we're looking at a one-dimensional signal right now, whereas MRI images are two-dimensional, and we'll get into how that is represented later in this session. And the second one is that once we introduce phase to the Fourier transform, we need to start considering complex numbers, because each of these functions, the green, blue, and orange lines in frequency space, is then represented not just by amplitude, but by a complex number with a real and imaginary part. And that, again, is just getting a bit too far into the math for the purposes of this course. It is all explainable, and I hope that skipping that information isn't confusing anybody, but it does get a lot more complex when we talk about, or when we start considering phase information as well. So I'm just going to kind of leave it here for now, and I'm confident that this amount of information is enough for us to kind of understand what's going on in MRI, and that's really what I'm trying to get across to you without losing anybody during these sessions. All right, so we have a bit of practice for understanding how signals are represented in frequency space. I'm going to try using Menti for anybody who has a phone or is watching this on their computer. I guess I'll just bring this up on my tablet. So actually, I'll go back for a second. So the idea here is just if we have this signal in frequency space, I've got this example. I want to ask you to tell me what a different signal might look like relative to the red signal here. So there'll be some images on Menti that will hopefully help explain this. But yeah, let's jump into it and kind of discuss it as we go. All right. So if you haven't used Menti before, I imagine most of you have, but if you just go to the Menti website, like it says at the top of the screen here, and use this code at the top, 5178004. It doesn't need spaces in it. I checked. You'll get a little multiple choice box showing this signal here and asking you where you would represent, or how you would represent this signal relative to the 3 Hertz signal that I had drawn on the screen before. So just remembering that frequencies higher than the red line would be on the right, and lower would be on the left. And there's also amplitude to consider as well. And we just got 2 of these questions, but hopefully it'll help you kind of flex this possibly new knowledge set that you've gained. I'll just give like 30 seconds or so. Yeah, now that you guys, so I'll write down the number 5178004. Sorry, I forgot if I had this example on the 90 slide as well. I'm just writing down the code in case anyone still needs it. I'll need to go back to actually check the answers, but that's fine. All right, so let's check the answers that we've got so far for this one. I should just press S and we'll see what we get. Oh, you can get the images, nice. Aha, yes, most of you are correct. Glad that kind of came through. So the answer here, and I did try to draw these little diagrams to scale. Since the blue frequency here is a higher frequency than 3 Hertz, you can see how it's cycling quite a few times in the same amount of time as the red signal, which I'll just pull up again for a second. Since that red signal is a lower frequency, we can expect the blue one to be represented to the right in frequency space. So it would be a higher frequency. And then the other thing to catch is that the amplitude of the blue signal would be higher than the red one. Sorry, I realize now that switching to Menti, I didn't actually include the red signal for reference here, but it was I drew the blue signal at a higher amplitude, so the actual line of of the blue signal would be higher as well, just to represent that. Okay, so we're figuring this out as a team, obviously. And let's jump to the second question, which when I switch slides, you should get a new prompt on your phone or browser, whichever one you're using. Same question. So the red signal is the same. I'm actually just going to like split my screen here. Hopefully it doesn't look too bad, just to show you guys the red signal to hopefully correct my mistake a little bit. And then there's another multiple choice to try and represent this green signal. And again, we'll just give like 30 seconds for you to think about it. All right, sweet. Let's say that's enough for this brief exercise. Let us check the answers for this one. Okay, yeah, again, largely correct. Great job, everybody. The correct answer here is C. So the reason for that, I guess I'll just kind of do the same thing I was doing before. The reason for that is our green signal is lower in frequency than red. I can just kind of pull that up again for you. Yeah, so comparing the two, we see that the red signal that I've drawn here cycles 2.5 times, whereas the green signal cycles 1.5 times. So it's definitely lower frequency, which means that the function in frequency space would be represented to the left in the lower frequency area compared to the red signal. And then its amplitude is also much lower as well. And that's why the green line is also shorter than the red line. To those of you that answered A, that is incorrect just because frequencies represented in, signals represented in frequency space are always positive, just because they're representing the magnitude of the amplitude. If we want to represent a negative frequency, which is definitely possible, like that would be, here I've drawn a sine wave again, starting at 0 and going up and then down. But if we had a cosine wave or anti-sine wave or something like that, then we could see a signal vary in the other direction. Instead of being an amplitude marched to the negative side, like I had in question A, that signal could just be represented either at a different phase or to the left of the origin, I guess, in frequency space. So it would be represented as a negative frequency. But that's a little bit of extra nuance that we don't really need to focus on too much. The main thing that I wanted to pull here is that left to right represents actual frequencies, and bottom to top is the magnitude or amplitude of that frequency. So great job, everybody. And if this is your first time kind of getting into frequency space, I have good news for you. That's the end of the questions, and it becomes a bit more natural over time as well. All right, cool. Thanks for going through that exercise with me, everyone. Let's move on. But again, if anyone has any questions about frequency space, great, just let me know. So this is the first time that we're going to kind of be putting all of our knowledge together into talking about what actually happens during an MRI sequence. That's drawn on this 5-lined diagram called a pulse sequence diagram. And I'm just going to kind of walk you through this. If we get there later in the presentation, which I imagine we will, I'm going to ask you guys to walk me through a similar diagram, given a couple prompts with some extra knowledge that we will have gained by that point. So anything that you pick up here will be relatively useful at the end of the presentation as well. No pressure, of course. This is my volunteer time and your volunteer attendance, so it's not like a pop quiz or anything, but I thought it might be a more engaging way to kind of reinforce these concepts. Okay, so once we have our brain, our body of interest in the MRI scanner, we need to essentially use all of the different magnetic fields and gradients that we have learned about in a certain order in order to actually like prepare our signal and then collect it. So let's kind of talk about the different lines that I've got here. First of all, at the top, there's one labeled R.F. That stands for radio frequency, and it's representing the pulses, the actual tips to the NMV that we are applying. Most of our examples so far, in fact, all of them have been using a 90-degree pulse. So applying that B1 magnetic field to tip the net magnetization vector fully into the transverse plane, that 90 degrees from its starting point to its end point. So I'll draw one of those here because we know that is the first thing that we need to do to tip our NMV into the transverse plane. And then after that, we're going to do the spatial encoding and we're going to record signal. The reason that this is a radio frequency, the reason that it's labeled as RF is because the typical range of frequencies that a B1 field is applied at is in the radio frequency range. So in the hundreds of megahertz range, I think, just off the top of my head. And we talked about why that is in the past with the Larmor equation. Our B1 fields tend to be applied in the radio frequency range, hence the RF label here. That's fairly standard. Next, we have our slice selection line. That's the purple second line, S.S. And this is our gradient in the Z direction conventionally, from bottom to top of the head or other body of interest. And this is where I'm going to be representing when we use those gradients. Third is our phase encoding or PE line, again, where I'm going to be representing when we would apply a phase encoding gradient. Fourth is our frequency encoding gradient line. Again, just kind of representing the gradients that we use in the X direction conventionally or typically. And then the bottom line is when we are actually recording signal. Because we could record signal at any point after we've tipped the NMV into the transverse plane, but it's not really useful until later. So that we have a line in this pulse sequence diagram to represent when we would actually acquire signal to keep track of when we actually have meaningful signal to collect. Okay, so in order for this 90-degree pulse to actually mean anything to us, we don't want to tip the NMV from the entire brain, right? So we're going to be applying a slice selection gradient at the same time as the radio frequency pulse. And how I'm going to represent that is with a box. At the x-axis on this graph is time, as I've got drawn at the bottom here, and the y-axis here that I'm drawing on is essentially the amplitude of the gradient, which is kind of arbitrary. I'll use amplitude a couple ways during these pulse sequence diagrams, but essentially it's just my choice of how tall I want these boxes to be. So the box here is representing when the slice selection gradient is turned on, and then sorry, just circle that there. And then the duration that it's on is basically the width of the box, and then when it's turned off, the box truncates. I guess it closes off. So it's essentially representing the magnitude of the gradient and when it is turned on and off. And you can see that I've attempted to get the slice selection gradient to turn on when the RF pulse begins, and then end when the RF pulse ends. Didn't quite get there, but close enough for our purposes. So this is showing us that the slice selection gradient has to be on for the entire duration of the RF pulse in order to effectively tip the NMV just in that one slice that we wanted to record from. Just gonna get rid of these little dotted lines. So we've got a bunch of other stuff to add. I don't want it to get too complicated. So after we've tipped the NMV, we've encoded our Z axis information, and we still need to do phase encoding and frequency encoding. Those lines are still empty, and we need to apply gradients there in order to encode information in the X and Y directions. And after that, we can record signal. Now, we're going to do our phase encoding gradient first. So I will just draw that out here in our orange. And it'll be just a positive gradient here. And that essentially, this positive gradient, I'm just going to kind of expand over here. This essentially is saying that we've got a positive gradient with some magnitude, right? That's determined by the height of the box. This is basically all that's representing is that in the y direction, we've got a gradient that has that's applying or encoding phase such that the spins that are kind of further along the y direction are going to be ahead in phase, and the ones at the in the negative y direction are going to be behind in phase. And we'll dig a little bit into that later on. But we can do that whenever we want, right? So it doesn't hurt to do the phase encoding gradient right away, because we just need to encode that phase, and then we can turn the phase encoding gradient off, and that phase is going to be preserved until we're ready to record signal, because there's not going to be any other gradients that are going to reverse that phase encoding in the y direction. It'll just stay there and be present in our signal when we record it. Hopefully that makes sense for everybody. And then lastly, where you need to encode our frequency encoding information, right? Using our frequency encoding gradient. Sorry, I don't want to just keep rambling using the same words over and over again. This one tends to be longer than the phase encoding gradient because it has to be on for the entire time that we're recording signal. And recording signal does take some time. So we can just kind of shoot like a little bit of phase in there with a phase encoding gradient, but then our frequency encoding step typically takes more time. So all is fine and dandy so far. Then, oh, sorry, I just had a hair on my screen. I'm going to represent the signal that we are actually recording as an echo, which perhaps you've been exposed to before. Close enough. These, I've never got a good method for drawing an echo, so anything that's close to this like envelope of increase and then decrease, I will take, even if it's not perfect. I've got a picture like in the next slide, I guess, to show you what an echo actually looks like. Now, the reason that we are collecting an echo is because we have some other work to do in this pulse sequence diagram that I haven't alluded to yet. The problem here is I've already talked about how we can apply a phase encoding gradient to get some spins to be ahead in phase and some spins to be behind in phase in the y direction, which is great. That's what we want. But phase encoding or phase differences, excuse me, are just they are caused by a gradient being on, right? And that's not exclusive to the y direction. That can occur in any direction, which means that our slice selection gradient here and our frequency encoding gradient there are also introducing phase differences, which is bad because, like I talked about earlier, we only want to see our frequency encoding differences in the x direction and our phase encoding differences in the y direction. So what we do here in order to actually reverse the phase differences that are caused just by the the purple and blue gradients here being turned on is we are going to apply a negative gradient in that same direction to reverse the phase. And what that looks like is something like this. So I've tried to draw a slice section gradient that is negative for the same duration as it is positive. And that's going to, in a perfect world, reverse all of our phase differences in the z direction, or slice selection direction. Although in reality, what we can do is reverse our phase differences in the z direction in a quicker time period by applying a gradient that is something like twice as strong, so twice as tall, and half as long, or thereabouts. Something like that. I'm not going to draw it again, but hopefully you get the kind of idea. The determining factor here of how phase differences are accrued by spins in a direction is essentially the area of the box. So like the area under the curve, or just like the duration and magnitude of a gradient. So essentially, so long as the area in this first box equals the area in this second box, our phase differences, again, in a perfect world, will be canceled out. So we can apply a gradient for half as long, so long as it's twice as strong, which is fine in the slice selection direction. Typically, for frequency encoding, which we also need to reverse, we're already kind of near the maximum of our frequency encoding gradient to maximize those differences. So instead, we are going to be keeping the magnitude relatively similar, and then applying the negative gradient here. That looks about right. You can see I have intended to draw our negative frequency encoding lobe before the actual signal recording, and also for half of the duration of the actual signal recording. Now this is done on purpose in order for some phase differences to be accrued in the negative x direction, and then that phase encoding is going to be reversed during our readout, and then every part of our signal is going to be in phase again at the middle of our frequency encoding gradient and our signal readout, and then things are going to dephase again on the negative lobe. So essentially, yeah, I guess I can kind of write this out. Just going to make it a little bit bigger and our pen a little bit smaller so that my writing isn't quite as cramped. This gradient is intended to cause dephasing in the x direction. And then this first half of our frequency encoding gradient and our readout is going to be where our signal is rephasing. And then on the second half, it's going to be dephasing again. Hopefully that makes sense. If not, feel free to ask me questions about it. Happy to try again if I haven't been clear enough the first time. But this results in an echo in our signal. That's typically what it's called, while signal is kind of going from out of phase into phase and then back out of phase. We get this kind of envelope shape where our signal is increasing amplitude and then decreasing in amplitude. And this is essentially the best we can hope for, because with a gradient like this on, we're always going to be incurring some phase differences. There's no way to avoid that, just because of the way gradients work. So instead, what we do is we balance our signal and collect an echo instead, which has this kind of envelope-like appearance. And that is our very first simple pulse sequence. Let's see if I missed anything important here. Nope, that's basically it. So at the top here, I've got a label to make sure I don't forget. This is a gradient echo sequence. Let's make this pen thicker again. Gradient echo. This is reasonably common, but typically in MRI we use spin echo instead of gradient echo, which we will talk about very soon. But this is one way to prepare to actually do a pulse sequence on an MRI scanner to record an echo that actually means something using just gradients. The reason it's called gradient echo is because we are correcting for the dephasing that we have incurred with our slice selection and frequency encoding gradients using negative gradients. So we're just relying on gradients to dephase and rephase our signal. That's all that we're using. So that's what gradient echo means. Now, another extra nuance is that this signal that we've drawn here is from one slice of the brain and also only one phase condition. So in reality, we're going to need to redo this pulse sequence many times to collect full information from one slice, and then do it again and again with different slice selection gradients in order to collect information from multiple slices in the same brain. And this essentially is where time can kind of add up and cause our MRI sequences to take minutes instead of just milliseconds, because we need to do the same pulses again and again under different conditions to collect information from other parts of the brain, which might be a little bit unclear. Hopefully, once we get through how this information is stored, things will make a little bit more sense. But for now, these three dots on the right side of the pulse sequence are representing that there's some passage of time before this whole thing is repeated again. So we would over here have another 90-degree pulse, and then we would have another slice selection gradient that is co-occurring with that 90-degree pulse, and then everything else would be to the right of the diagram that I haven't drawn here. So we're repeating the same sequence again to collect more information. And there's a couple key parameters, I guess, to mention here. That is TR and TE, which if you've been exposed to MRI, you've probably run across those abbreviations. So let's dig into them. TR, first of all, stands for repetition time. So we'll start making notes over here. And TR is the amount of time between these 90-degree pulses, the amount of time that you wait until you repeat the pulse sequence. You start working with the magnetization vector again. So that would essentially be from the start of this pulse to the start of that pulse. That is our TR. And this is a key parameter that we mess around with in order to get different contrasts from tissues, which we'll dig into possibly at the end of this session and definitely next session when we're talking about how this is all actually used in actual MRI sequences. The other key parameter is TE, which stands for echo time. This is another really important time that we can mess around with, another important parameter. And this is the amount of time from the start of our sequence to when we collect the peak signal, when we collect the center of our echo. So that would be, see how straight I can draw a dotted line. From around here at the start of our 90-degree pulse to the center of our echo, which is approximately there. Hopefully that's close enough for you guys to understand what I'm talking about. This is TE. So it is shorter than TR, of course, because it's somewhere in the middle of our pulse sequence or near the end of our pulse sequence, whereas the TR is the amount of time it takes for us to actually repeat the pulse sequence. So these are two very important parameters that will come up all the time when we're talking about pulse sequences, and those are their definitions. Yeah, we'll save extra detail until the appropriate time. Okay, so a couple other notes that I wanted to make sure I didn't miss here is we need to repeat this sequence multiple times. Let's put many times here for the reasons that I've already discussed, and I'll flesh that out when I'm passing the notes to you guys. And also another important thing, we talked about T2, well, in both previous sessions, but in detail last session, and talked about how there are imperfections in the scanner and additional features that cause us to measure T2 star instead of T2. So in this example with a gradient echo sequence, we are measuring T2 star, not T2. And what I mean when I say that is the amount of signal that we have left in our echo at any given echo time is determined by T2 star dephasing, which again is how it's that process by which spins go from in phase in the NMV to out of phase as some spin faster and some spin lower, or spin slower. T2 star adds in extra imperfections like how the gradients we apply are not going to be perfect. There's going to be extra differences between tissues like bone and air, and there's going to be other conductive elements in the body, and all those things cause extra dephasing that is not simply due to spin dephasing. So that's one of the drawbacks of gradient echo, is that we're losing signal faster than we could be because we're on that T2 star curve, which takes a nosedive real fast, and our signal disappears very, very quickly. But gradient echo can kind of account for that because it's fairly fast, and that'll kind of come up later when we talk about spin echo. Next thing I'm talking about is the echo and spin echo, and we're at 2:05. I know I started a little bit late, but let's do a break here. It might as well. We're making pretty good time, I would say. So I'll give us a 10-minute break. That's fine. So we'll come back here at 2:15 to cover spin echo and K-space, which will just be so much fun. And then we'll wrap up around 3. I'm not going to keep you guys late just because I started late. So break time until 2:15. All right, we are back to recording. So I will start rambling again. Had somebody asked to just kind of give a quick recap of this whole mess, so I will do my best. There is a fair amount of info in here, so might not cover everything as comprehensively as I did the first time, but hopefully the small refresher helps for everybody. So this is the first time we've encountered a pulse sequence diagram, and this is essentially showing us how we're using RF pulses, which is our B1 fields, to tip the NMB, and the gradients that we're using to encode spatial information in the X, Y, and Z directions. And then from left to right is representing time. So earlier stuff's happening on the left and later stuff is happening on the right. Essentially what I've shown here is when we apply our 90-degree pulse with that B1 field to tip the NMB, we need to have our slice selection gradient on at the same time in order to tip the NMB only in one slice of the brain or other body of interest. And then after that, we need to apply our phase encoding and frequency encoding directions, or gradients, which are the orange and blue lines, to get our spins to have different phases and spinning at different frequencies. And once we've done that, then we can collect our signal, which is represented by this echo, that red wiggly line at the bottom. And that's what we're going to talk about next. The other important part of this diagram is that we introduce differences in phase in any direction when we turn a gradient on. So we need to apply negative gradients, or the opposite of our slice selection and frequency encoding gradients, in order to counteract that phase that we don't want to be accrued or to be encoded in that direction. And that's what the boxes that are kind of below each line represent. And that allows us to collect this echo, which is going to be a signal that we see as spins or protons that we're collecting signal from. They come into phase in the first half. They become maximally aligned right in the middle. That's why it's highest amplitude there. And then they go out of phase. They dephase again on the second half of the echo. So that's kind of the broad overview of the pulse sequence diagram. You'll see a few more of these when we talk about spin echo and maybe a T2-weighted sequence at the end, but they'll come up throughout the rest of the sessions. And in the interest of time, I'm going to jump forward to make sure that we cover some other stuff during the second half of the lecture. But hopefully that helped. I'm, again, happy to answer any questions if they're in chat or over audio. Totally fine. So this is what an echo might actually look like. If you compare to my drawing above, B+, I think. But yeah, the actual representation of the echo is much more symmetrical and higher frequency than my own drawing. And we've already kind of talked about why we focus on collecting an echo in MRI. I just wanted to give myself space to write this out so that it kind of gets hammered home for everybody. So the first reason that we collect an echo in MRI is because it balances out, I'm going to call it undesired dephasing, because we want spins to be dephased in the Y direction. Typically, that's how we tell the difference in signal in that direction. But we don't want dephasing in the X or Z direction. So just by applying gradients in such a way that we can balance that out, we get this echo, where we have rephasing and dephasing lobes of this envelope. Another thing that is important about the echo is because we're actually rephasing the signal and we're trying to counteract any dephasing that has happened, dephasing causes our signal to decrease. So by rephasing all of our signal into an echo, that actually maximizes the signal that we can get at any given time. So I'm going to write that out as maximizes signal measured at t. And you can see already I'm using TE to represent the time that we're acquiring signal. That's kind of like generally what it means, although obviously it's not, we're collecting signal over a period of time, not just one time, but TE helps us to quantify the actual time that we record signal. So at any given time that we record signal at any given TE, if we dephase, or sorry, if we rephase our signal at that time, we'll have more signal to measure. So this is why we record an echo instead of like just that free-flowing FID curve that I've showed before, which is something like this. This is kind of what you would record if you didn't do any spatial encoding and you just recorded the signal after you tip the NMB. You get this FID curve, which looks kind of like the dephasing half of a gradient echo or spin echo. But we're losing signal that whole time that we're recording from the FID curve. Whereas if we use the gradient, or sorry, if we use the echo, then we maximize the signal kind of across the recording period. Now, there are different kinds of echoes. We have already talked about gradient echo, which is highlighted on this image that I've pulled from a great website that will get a shout out later. I'm writing image, but I mean to be writing echo. And there's also spin echo, which is very common. It's kind of like the counterpart to gradient echo. I would say it's actually more common than gradient echo. It has some advantages. And let's kind of dig into that right now. I'll keep the shoddily drawn FID curve here. I'm gonna flesh that out later. But let's jump into what a spin echo does. So this adds one more layer of complexity, but is very important for many different sequences that we're going to talk about next time. The concept in spin echo is that instead of rephasing our spins for the echo with gradients, using those negative gradients to reverse dephasing that we had in the gradient echo pulse sequence diagram above, what we're going to do is use a 180-degree RF pulse to kind of switch the spins around, essentially. And then those that are spinning faster will be behind in phase, and those that are spinning slower will be ahead in phase. And this helps things to kind of all rephase naturally. I'm kind of debating what to talk about first. Tough one. Okay, another benefit here is in spin echo. Actually, let's talk about spin echo first, or like actually show the visuals first. Sorry, you'd think I would have like been happy with my decision yesterday, but I was not. So can I make this larger? Not really. Great, that just made everything black. Sure, this helps us to focus on it, I guess. So if we can kind of look at this diagram from Wikipedia, which we're all familiar with, first we have a 90-degree pulse, then our spins begin to dephase, then the 180-degree pulse actually flips everything around, and like I said, helps us out with rephasing because spins that were getting ahead in phase are now behind, and by processing faster, they will catch up again. And spins that were processing slower and falling behind, they're now ahead, and they'll kind of lose that lead over time as the faster spins catch up. This isn't the only visualization I've got, but it's, I guess, the most like accurate to MRI. Let's go over to a tortoise and the hare diagram, if I can figure out how to exit this. I don't know, I can't, we're just stuck here forever. Sorry, everyone. This is just the end of the presentation. Now we're just gonna be watching that bulb forever. Okay, so back to the MIOS webpage. Here is another visualization of the same kind of thing that Wikipedia had, but without the pulse sequence below it. So we've got a 90-degree pulse, then we have some relaxation where that dephasing happens thanks to our T2 mechanisms. We have our 180-degree pulse, which reverses who was ahead and who was behind in dephasing. I'm just going to play it one more time for us. And in that way, we kind of cause our spins to rephase more naturally. Obviously, you can see in this diagram, it's not perfect, which is accurate to MR, but it is definitely advantageous in a couple ways. I'll display it one more time, and then we can move on. The old MIOS webpage had different colored arrows for faster and slower, which I thought helped, but apparently they did not keep that when they moved to videos. All right, so on to our tortoise and the hare example. This is what MIOS uses, and I think it makes a fair amount of sense. If the rabbit in this example is the spins that are processing faster, it's essentially going to get further along in this race than the tortoise does until the 180-degree pulse is introduced, which reverses where the finish line is, essentially. That's what this diagram is showing, is essentially both of them get as far as they're going to get over a given time period, and then when the 180-degree pulse is introduced, they turn around and they both have to race to the finish line. And because they're moving at the same speed, we're just considering their precession rates to be constants here, they're going to reach the finish line at the exact same time. And that's what rephasing is when we're considering spin echo. So hopefully that also helps make a little bit more sense. I don't know what this animation is, so we'll just skip it. So what this looks like in spin echo is similar to gradient echo. I'll just kind of draw a couple things out more quickly this time. So we've got our 90-degree pulse to tip the NMB in a given slice. We're choosing that slice with our selection gradient with a negative lobe of some kind. And then we've got our phase encoding set of gradients. I'm going to start drawing this as a circle now. We'll dig into Y in a little bit. And then we've got our frequency encoding gradient. I'm going to draw that right underneath the phase encoding gradient. Now, the reason for this frequency encoding gradient being under the phase encoding gradient is it saves us time. And this is the portion of the frequency encoding gradient that we're using to dephase spins before we rephase them in our actual readout. So instead of being a negative lobe, this time it's positive. And the reason for that will soon become clear. But it doesn't matter if our frequency and phase encoding gradients are on at the same time because they are being applied in orthogonal directions. The only limitation there is how much power the MRI scanner has. Turns out MRI scanners have plenty of power, so they can do both gradients at once by design. Now, the next thing that we're going to do is introduce our 180-degree pulse, which I'm going to draw with a higher amplitude and marked out so that we all know that's what I'm attempting to draw. And then we wait a certain amount of time that's approximately the same as our 9-degree pulse. In fact, to make that more clear, I'm going to move that 180-degree back just a little bit. And then we can just record our signal after we wait long enough for our spins to rephase naturally. So when we're recording our signal, again, we have to have our frequency encoding gradient on. And this is attempting to be about twice the duration as our first dephasing gradient. The last thing that I have to draw here is our signal. Oh, that echo could use some work. It is sparse in the middle. But anyway, so this is what a spin echo pulse sequence looks like. Couple things to kind of note here. A big benefit of spin echo sequences is that we are now measuring T2, not T2 star. That's big. We are able to measure signal that is decaying only because of those spin-spin dephasing interactions that we want to kind of factor into our imaging sequences. And we remove the effect of all of those imperfections in the main magnetic field and in our gradients and everything else that I've talked about a couple times with that is encompassed by T2 star. The reason for this is because any imperfections in precession frequency that are introduced by those unpredictable error factors that T2 star includes, their effects balance themselves out after the 180-degree pulse. Excuse me. That's because once we flip everything around and we have the spins that are precessing faster behind in phase and the spins that are slower ahead in phase, those same variations in precession frequency are going to, those differences in precession frequency are going to be constant, which means that the ones that were precessing faster will continue to precess faster and they will catch up to that point where everything's in phase again. And likewise for the other half of the equation. So our spin echo, our 180-degree pulse, actually just causes all of those imperfections in our scanner to balance themselves out by accounting for differences in precession frequency that are driven by stuff like imperfect gradients. Now, another benefit of spin echo is that we can use the exact same gradient. You see how this frequency encoding gradient, let's highlight it in purple, I suppose. Oh, that is definitely orange. This frequency encoding gradient that's introducing dephasing is positive. And so is our frequency encoding gradient that we apply during readout. Now, the reason that we can do this is because, again, with that 180-degree pulse, everything gets reversed, it gets turned on its head, and then the positive frequency encoding gradient helps those signals to rephase and dephase. It reverses the effects of the first positive frequency encoding gradient. Now, this is important because no gradient in MRI is perfect, which means that if we had a positive frequency encoding gradient and a negative frequency encoding gradient, like we did in the gradient echo example, those gradients are not going to 100% perfectly cancel each other out because of just machine error, because the coils of the gradient cannot be aligned perfectly, or any other machine factors that could contribute to gradients not being 100% perfect. They're always going to be imperfect in some way, just in terms of the slope of their change in magnitude from negative to positive. So by using spin echo, we account for those imperfections in the gradient, and that helps us to kind of maintain more signal and not lose signal more quickly like we do when we're looking at T2 star based sequences. So that's another big benefit of spin echo. So I just want to be back to black so I can say we can use the same gradients. Same gradient polarity, both positive. Oh, that's an A. Polarity, yeah, meaning positive or negative. Same gradient polarity to reverse, well, to dephase and rephase, to use the language I've been using so far. All right, hopefully that makes sense. That's a big benefit of spin echo. Now, the downside is that spin echo takes a little bit more time. It is going to have a longer TE and a longer TR. So let me just write that out. And the reason for that is because we need to wait a given amount of time in order for whatever dephasing that happened before the 180-degree pulse. We need to wait that same amount of time after the 180-degree pulse in order for the spins to kind of naturally have the same amount of time to balance out their dephasing. You know, like if it takes 50 milliseconds for, or if we have 50 milliseconds before our 180-degree pulse and then we flip everything on its head, we need to wait 50 milliseconds for those exact same processes to cancel themselves out. So we're kind of, in a sense, doubling the amount of time that it takes for us to prepare and record a signal, which you would imagine would decrease the amount of signal we have available thanks to T2 mechanisms. And it does, but this is kind of balanced out by the fact that we're now measuring on the T2 decay curve, not the T2 star decay curve, because T2 star signal is, or T2 star dephasing causes signal to be lost much more rapidly. So it's not as big of a drawback in terms of signal available, but it is a big drawback in terms of the amount of time that it takes for us to complete an MRI scan. Spin echo takes longer just kind of by definition and by the way that dephasing and rephasing works in spin echo, but it has some big advantages as well. Okay, the last thing that I want to touch on in this spin echo sequence is the fact that I have drawn our phase encoding gradient as a circle, which I'm circling in green now. This is to represent that we are going to be repeating our sequence, our pulse sequence diagram here many times, and we need to use different phase encoding gradients during each of those repetitions in order to kind of collect information about signal in a slice at different phase conditions. So some conditions where the phase encoding gradient is weakly positive or weakly negative. You know, for any given sequence, for any given iteration of this pulse sequence, we're only going to have a phase encoding gradient that, is at one of these settings in the little ball that I drew before. But it's typically represented as a circle just to show that we're varying our phase encoding gradient in order to collect information from spins at different phase encoding frequencies. So as we repeat this, we're going to be using different gradients. I'm just kind of like briefly drawing and disappearing to visualize what that might look like, to incur different phase differences and then record that signal again. This is very important for us to actually interpret where signal is coming from in a slice, though I haven't exactly talked about why yet. I think it makes more sense once we talk about k-space, which is, I think, next in our talk for today, probably what we're going to end on. But intuitively, k-space can be confusing, as we may see. Intuitively, the reason that we have to collect information or signal from the brain in different phase conditions is because it's difficult to tell the difference between signals at different phases and just signals at different frequencies. So if we just have one phase encoding condition and one frequency encoding condition, the Fourier transform is going to have trouble distinguishing between whether the main signal that we see at any given point in that echo is driven by a combination of signals at different frequencies and amplitudes, like we've been talking about so far, or signals that are more similar, like the exact same signal with the same frequency at different phases. So in order to kind of help us tease apart the phase side of that equation, what we need to do is repeatedly vary our phase condition with different gradient amplitudes, both positive and negative, and then put all of that information in a two-dimensional phase and frequency space into our Fourier transform, which helps us build an MRI image. So let's talk about how that is actually done. This is where people are most frequently lost in MRI physics, and I am going to do my best to walk us through it and just get us through the main properties of this thing called k-space that are useful to understand without talking about a lot of the nuance that is important if you want to go further, but possibly too much for an introductory series like this is. So k-space. What we've been talking about so far with the Fourier transform has been a one-dimensional signal, right? Like one echo or one time-varying signal like I had in that diagram of the Fourier transform before. But the problem is that anything that we're imaging in MRI is going to be a two-dimensional image. And this requires us to put a two-dimensional set of data into the Fourier transform in order to compute a two-dimensional image. And the math behind this gets much more complicated than you would see with a one-dimensional signal. So I like talking about the Fourier transform in one dimension because it makes the most sense. But in reality, in MRI, what we were doing is we were putting in a two-dimensional set of imaging data, all these different echoes that we've collected into the Fourier transform, and it's giving us a 2D image on the other side. Now, we've been talking, and we had those Menti questions about frequency space that was all in one dimension, right? Where we just had an axis with lines that were representing frequencies at different, that were representing signals at different frequencies in the time domain. K-space is just two-dimensional frequency space. So if I could just explicitly tell you what that means, in MRI, the x direction, or the kx direction this way, just to denote that we are in k-space. This represents differences in frequency. And I bet you know what's coming in the y direction, don't you? This direction, or the ky direction, is representing differences in phase, different phase conditions. So the reason that we're varying our phase gradient in that previous example, or any pulse sequence, is because we need to fill out different lines of k-space in the y direction in order to collect a two-dimensional set of information that will allow us to compute a two-dimensional image. Okay, most of well, all but one of these figures in this session are from, or this section, the K-space section, are from this website called mriquestions.com. It looks like it's out of the 90s or early 2000s, but it is probably the best resource I found online for more technical MRI questions these days. Anytime I'm looking for an explanation on what is even going on in MRI, which is frequent, I go to MRI questions first. The questions and the concepts are explained very well, kind of a little bit above the level of these sessions, but I think if you follow along with these sessions, you're pretty much primed to understand what they're talking about. So good website, definitely a good resource for anybody who needs to study MRI physics at whatever degree that we need to. Okay, so now I'm going to walk us through what K-space actually is, again, without getting things to be too confusing. So the first thing that I want to talk about is how each line in K-space represents one echo that we collect under different phase encoding conditions. All right, the reason for this is essentially, so each of these little green lines is one echo. And the reason that we're varying our phase encoding rather than our frequency encoding information is that it's much easier to apply or to encode different amounts of phase to spins in the y direction than it is to vary our frequency in the x direction. Just because, like, when we're doing readout, we want as much contrast as possible in the x direction, so we're going to be applying that gradient at the maximum amplitude. And if we apply it to the maximum amplitude, the only way to, oh, that's not even a thing actually. Sorry, I just kind of talked myself into a circle and reached an incorrect conclusion. But let me go back here and say, if we want to vary our phase encoding information, all we need to do is either apply a phase encoding gradient of a different magnitude, which is what's being done in this example, where each of these boxes is a different height, either positive or negative. Or we can apply the same phase encoding gradient magnitude and wait a different amount of time, which is another option, although that typically tends to lengthen MRI scans, so it's not typically done. It is possible though. Another advantage of doing different phase conditions is that we can encode that phase information whenever we want. So we don't need to be doing that just when we're recording signal. But the main takeaway of this figure here is that when we're collecting information for a two-dimensional K-space, each of the lines in K-space represents one echo that we collect. And the differences between those echoes are determined by how much phase you encode in the y direction. So the magnitude of that phase encoding gradient. And that's why I was drawing that as a ball previously. Okay, so that's the first key takeaway from K-space, is that each line of K-space is one echo. And if we kind of go back up, you can see that there's like bright and dark spots in K-space from left to right and top to bottom. This can kind of be understood by thinking about looking at the echo from the top down. So when the echo is largely positive, the dot in K-space is bright. When it's negative, the dot in K-space is dark. And you can see that there's kind of a brighter center in K-space because that's when the echo is at its maximum amplitude generally. Although you can see back down on this second diagram that when we have a greater amount of phase differences that are incurred by a stronger phase encoding gradient, we lose that signal fairly quickly and our echo becomes smaller in amplitude overall. And that's why the outsides of K-space are darker. But again, that might be too much nuance. Probably could have skipped that part. Now, in terms of how the Fourier transform works with this information of the different echoes that we are collecting in K-space, this is always kind of like, and this one always blows my mind a little bit. But the way that this information in K-space is interpreted in the Fourier transform to take this information and move it into an image is each dot in K-space represents a spatial frequency. And what spatial frequency means is instead of having, that signal wave with its ups and downs, like you might see on a radio wave or something like that, a spatial frequency instead is in an image a change between dark and light and dark and light and dark and light, as you can see in this kind of like red overlay on, oh, that's not even my line. Okay, on the MRI image on the right side, there's this transition between dark and light and dark and light, and that's the spatial frequency. It looks like a fairly high spatial frequency here because it's changing quite often. And that frequency that's overlaid on top of the brain is represented by that red box. That dot or that region of K-space is telling the Fourier transform how much of this specific spatial frequency is present in our image. And you can see that the angle of orientation of this spatial frequency is determined by basically the angle between the x-axis in K-space or the k-x-axis and the point itself. That's what that kind of blue arc is showing you, which I can kind of quickly highlight. So this angle here is determining the angle of this spatial frequency that's kind of going from top right to bottom left or the other way around in K-space. So that's what this data is actually representing, is spatial frequencies in our MRI image. Fun times. And if you can hold that in your head, you're in a good spot. Although frequently I would lose like my sense of what this actually means and have to go back and relearn it. So no worries if this is getting a little bit too abstract for you. But this, I hope, helps to kind of drive this point home, is that each point in K-space represents a different spatial frequency. Okay, so somewhere up here looks similar to the spatial frequency we were just looking at in the top right there, although it's even higher frequency because it's even further out in K-space, and further out from the origin in K-space, which is in the middle, represents higher frequencies, similar to how lower frequencies in those Menti questions that I had were on the left of that axis and higher frequencies are on the right. Same kind of thing in two-dimensional K-space. So you can see in the top right is this very high spatial frequency oriented in that same direction that we were just looking at, whereas the one at the top middle here, that represents this very high frequency that's oriented just straight from top to bottom because it's on the KY axis, and so on and so forth. So we can think of the Fourier transform, or in fact, it's the inverse Fourier transform because we're moving from frequency space into image space. And it's no longer really time space because we're looking at a two-dimensional image, not a one-dimensional signal. But we use the inverse Fourier transform to move from frequency space or K-space into image space. And what that inverse Fourier transform is doing is taking all of these spatial frequencies that are represented in this gray, black and white box and sandwiching them together at the appropriate amplitude that's represented by how bright or how dark each pixel of K-space is. It's sandwiching all of those spatial frequencies together, and that, believe it or not, gives us the image that we're looking for. That gives us the image of the brain or the image of the knee or the heart or whatever. It's just by sandwiching together all of these different spatial frequencies. You can see that there are many, many points collected in K-space, so we have a lot of information to work with and a lot of nuance, and that can give us a really detailed look inside the body, which that's basically why the password to these sessions is MRI magic, because once you get to this level, it's kind of insane, the like things that we're doing to look inside the body. We have all these magnetic fields going on, and then this really fancy math and this like strangely abstract K-space, and then we're just all of a sudden there's a picture of the brain. It's kind of insane. Now this is the main takeaway from K-space. So I've talked to you a little bit about the properties of K-space. Each line represents an echo that we collect in MRI, and then we take all that information in K-space. We use the inverse Fourier transform to make an image. The main thing that any graduate student or anybody looking to understand like the fundamentals of MRI should understand about K-space is that the basic contrast of an image is in the center of K-space. That's where K-space is the brightest. That's where the center of the echo is, and that's where the low spatial frequencies are. If I just scroll back up for a minute here, you can see this point in kind of the middle right of the, let me make that green so it's really clear. This point in the middle right of our image is corresponding to this very low spatial frequency, right? It's dark on the outsides, it's bright in the middle. And then, considering all of those different frequencies at the center of K-space, that gives us this very, bright and dark, black and white, but blurry image of the brain in this example K-space. And then all of the fine details of K-space are represented by the higher spatial frequencies on the outside. So if you need to remember one thing about K-space, it is that the basic contrast and like the main bulk of the image is in the middle, and then the fine detail is in the outside of K-space. And that's really the main thing that you should be taking away from this. The other stuff above is kind of useful background information, but I understand if it gets complicated fast. I've definitely had to work hard to hold all of this stuff in my head sometimes. And that essentially is K-space. This topic used to have like a full 2-hour session devoted to it, and I realized that while I had to learn all that stuff in my classes, it's not useful for everybody. In fact, even this level of knowledge probably isn't useful even for every graduate student, depending on what your project is. But I did still keep this stuff in the session because I believe that it's useful to understand what is actually happening with the signal we collect in MRI, even if it's at this basic level of understanding that it goes into this really weird frequency space, and then we use some fancy math to create an image from that signal that we collect. That's fine if that's the level that you're getting at. And that's kind of where we're going to leave it for now. Although a more clear understanding of K-space will help you to understand things like image artifacts and some of the decisions we make when we're designing an MRI sequence. But I'm going to kind of leave that stuff to the side for now. I think it's more advanced and it might not be applicable to everybody, whereas I do think this is actually useful, especially when we're talking about how to understand pulse sequences. Part of the reason that I bring up K-space is because it actually becomes quite a bit easier for me anyway, and I hope for you, to understand pulse sequences when you understand how they interact with K-space. So the title of this slide is Gradients Move Us Through K-space, which is a weird thing to say, but it does hold value. So let me explain what I mean. Here I've got a gradient echo sequence that I drew and walked you guys through above. It's not a spin echo, it's just a gradient echo. There's no 180-degree pulse. So we're just using these negative gradients to dephase and rephase our signal, like I discussed. Now, we can actually discretely identify where the point that we're going to be recording is in K-space given a pulse sequence like this. Seems a little weird, but trust me, it does actually help to understand or like to kind of work your way through pulse sequences for other sequences like DTI and fMRI that we're going to talk about probably next session, definitely next session. So this is probably what I'm going to end on, and we're basically at the last little nugget of information for you guys. So I've got 4 time points highlighted here, and I'm going to tell you where we are in K-space at each of those points. And you can use the same logic to locate yourself in K-space when you see any pulse sequence diagram. Again, strange but true. So at time number 1, we've just done our net magnetization vector tip, right? We've applied that 90-degree pulse, which I can label here quickly. And this actually puts us into like a given slice of K-space, right? It's a slice of the brain that we're imaging, or a slice of the body, and that is represented by a slice of K-space information. So this actually puts us at the origin of K-space. Okay. So at time point 1, our data point that we would record is at the center of K-space. Now that kind of makes sense, and it's okay if this kind of goes over your head, but it might help some people. This kind of makes sense because at this point, we have all of the signal in that slice available to us, right? If we record it, we're going to see that FID curve. It's going to be bright, dark, And that's going to just be signal from the entire brain. That's generally the brightest part of K-space is right in the center. So that's why we kind of start in the center after our 90-degree pulse, is because we have all of the information available to us. Now, the second time point I've got is after our phase encoding gradient. And by convention, a positive gradient moves us, in a positive direction in K-space, either in the Y or X direction. A negative gradient moves us in the negative direction. So what that means for this example is after or during, I guess, the phase encoding gradient, we're going to move from our time point 1 location, which is the center of K-space. We're going to move ... upwards in the KY direction, because phase information is represented in the Y direction in phase space. Sorry, K space. This has been a monument to stumbling over my words today, hey? Okay, so after time point 2, we have applied a positive phase encoding gradient. So we move in the positive KY direction. And now we're up a little bit in K-space. The next thing that happens is we have this negative frequency encoding gradient. And that, as you may be able to follow by now, is going to move us left in K-space. Oh, not red. So this is after time point 3. We have moved in the negative KY direction, because we had a negative frequency encoding gradient. Didn't leave myself quite enough space. But that essentially is the result of our negative frequency encoding gradient. We've moved to the left. And then we're going to collect our echo, which again is going to fill one line of K-space, right? So when we have time point 4, where we're applying that full positive frequency encoding gradient, we're going to move to the right in K-space. And we know that with my diagram, the positive lobe of that frequency encoding gradient is twice as long as the negative lobe. So we're going to move twice as far, which takes us from the left edge of K-space all the way to the right edge, right? And while I'm on the edges of K-space, the amount of K-space that you collect is by design. It's whoever made the pulse sequence that decides that. K-space itself is infinite, but the bounding box represents the amount of data we're actually collecting in there, because at some point, the fine details on the outside of K-space aren't useful anymore, so we don't need to worry about them. But to wrap this up, the positive frequency encoding gradient that we've got happening between time point 3 and 4 moves us all the way to the right edge of our K-space that we've collected. And that's essentially how you can picture gradients moving us through K-space. This is essentially it. And then you can see that between time points 3 and 4, so in this section where we're actually moving across K-space, we're recording data. We're recording that echo, and that's what's filling in those points. As we move across K-space, we're kind of dragging our marker across K-space, and the information from the echo is just slotting right into that line. And then maybe we collect 128 lines of K-space or something. That would give us 128 voxels or in the Y direction. So we need to do this many times to fill out this K-space, box, excuse me. And then we would do that by varying the phase encoding gradient. So if we did the same thing, maybe at a different time point 2 with a negative phase encoding gradient now, like this, we would be moving down in K-space, maybe a little bit further because that gradient's a bit longer and larger. And then we would go to the left again, and then all the way to the right, and we'd fill in this line down here. We just repeat that again and again to fill in our K-space window, essentially. So that is my coverage of K-space. And the last thing that we need to understand to talk about actual sequences in MRI. I'm going to forgo, actually, no, I'll do a lecture summary. It's just, there's kind of like a lot of, it's hard to just briefly cover this stuff, these specific topics, but I'll do my best. So I'm going to walk us through what I talked about today. I have another feedback form if anyone has the time to fill it out. I'll just post that in now, actually. Same thing as before, just looking for a little bit of helpful feedback from you guys on how these sessions are going. Yeah, I need to be sending this to everybody. Okay, and then like I said, session 4, which is going to be like the last formal session. I have 5 planned, but 4 I think is enough to like actually cover the basics, and then after that we can dive into more specific stuff if people have specific questions. But after I go through the session summary, I'm going to kind of like ask for sequences that you would like to be covered. So if you want to leave any of those in chat, I can add them to the list. So we're definitely going to cover T1 weighted and T2 weighted sequences because they're simple and easy to kind of start with. Then we're going to cover DTI, which is my specialty and very relevant for lots of people, and fMRI as well, which similar, not my specialty, but very relevant for many people who are doing imaging research. If you have any other sequences that you want thrown in there, feel free to suggest. I'd be happy to cover them with you. As I've learned about many other sequences, that was kind of the, I don't know, my specialty in my PhD was different imaging sequences. But back to session 3. So we reviewed gradients in general. We talked about how we use them to encode information in the Z, the X, and the Y direction using slice selection, frequency encoding, and phase encoding, respectively. We talked about how once we've got these different phases and frequencies collected in this one big signal, this echo that we collect, we use the Fourier transform to tease apart from that main signal what frequencies are present and what phases of those frequencies are present. And this does get messy fast with complex numbers, so I kind of just left at the basics of differences in frequency because that's easy to understand and 100% accurate. We had a couple examples of what frequency space looks like in the one-dimension setting. And then I walked you guys through our first pulse sequence, which we'll see a couple more of these when we're talking about the actual imaging sequences themselves. This is kind of how they're represented, and it's a good way to highlight their strengths and weaknesses. So we've got our pulses and our gradients all laid out here. We've got our TR and our TE parameters on display, which are very important for MRI sequences. And we know that this is a gradient echo sequence, which is sensitive to T2 star decay, not T2. I talked a little bit about the echo and its benefits. It balances out our dephasing that we don't want, and it maximizes the signal that we can collect at any given time, any given TE. And then I talked about spin echo, which uses a 180-degree pulse to let us measure signal decay based upon T2, not T2 star. And it allows us to kind of cancel out any unwanted dephasing that we might have due to, B0 field imperfections, gradient imperfections, machine error, or conductive materials in the body. Anything like that gets removed when we use spin echo, although it does take a little bit more time. Then we walked a little bit through K-space. I did my best to make K-space approachable and only focus on the things that really matter about it. If anyone wants some more nuanced information about K-space, I'm happy to go there. It's just not necessarily worth it for everybody. And I talked about how each line of K-space is a separate echo that we collect, and we're varying the phase conditions of those echoes in order to fill different lines of K-space. I talked about how each data point in K-space represents one spatial frequency, and then we sandwich all of those different spatial frequencies that are in our collected K-space to create one image of the brain. And the main takeaway of K-space here is that the big blurry contrast of the image is in the middle, and the fine details, those edges of the brain and everything else, are on the outside of K-space. And that's really the main takeaway of K-space is that one point. And then I talked about how there's this relationship between the gradients we apply and our location in K-space, which is quite helpful when we're considering pulse sequences, which we will be doing a lot next session. And with that, I will end our MRI physics lecture today. Thanks again for bearing with me with the reschedule and for sticking around for this afternoon. Hopefully you guys learned something, and we'll be here 2 weeks from now to talk about the actual sequences and dig into, what MRI actually is when we're sitting down at the scanner. Pretty excited for that.